All right, if you've watched Sal Khan's awesome first two videos, there's several things that I'd like to kind of maybe clear up or change a little bit on what he said, or kind of fill in some holes. So first of all, we're talking about waves now. All the way up till this point throughout this whole year in physics, we've been talking about basically particle type physics, energy being transferred from like one particle to another, and momentum or energy or something like that. But it was always particles. It was bowling balls and cats and baseballs and all kinds of stuff that we were looking at. Now for the rest of the year, we're basically looking at energy being transported by waves. And if you remember the definition of wave, and if you have your books, you can look on page 70. A wave is a disturbance that propagates through a medium or space. Now, Sal Khan talked a lot about through space, and that would be like a light wave. Light is an example of a wave that can travel through space. But sound is a wave that needs to have a medium to travel through. So a lot of different waves need actually a medium that the energy moves through, and the medium maybe moves back and forth and so on. By the way, a wave that goes through a medium that actually needs a medium to go through, like sound must have a medium to travel through. Sound cannot travel through space. Sound must have a medium, air molecules to compress. So sound that needs a medium to go through is actually called a mechanical wave, and a mechanical wave. So just so you know that vocab term, there on this Next Jedi trial, there's actually a lot of vocab instead of math. So the other word that I wanted to just look at that we've used several times that he used and I'm going to use also is called propagation. Propagate is fancy words for moving. We've talked about motion throughout most of the year, and we've talked about moving or motion. Now with waves, waves move also, but we have to use a fancy word for it. Waves propagate through space, or they propagate through a medium. So I didn't want you to get messed up on that word. Propagate just means basically the wave moving. So just to review the two types of waves that he talked about, the first one that we have right here is called a transverse wave. It looks like this. A couple things that we wanted to point out about it that he already pointed out on it. He called this bottom, the downward displacement here, a trough, which is good. I believe he called the top part peaks. Generally what we call them is crests. So the top part would be crests, and the bottom parts would be called troughs. The amplitude is the height of the wave, but that's not the entire distance like this. He talked about that a little bit. It's just the height from the resting line up to the top of a crest, or it could be from the resting line down to the bottom to a trough. Either way is a fine way to measure the amplitude of a wave. He also talked about the wavelength, which is given by the Greek letter lambda. And the way you find a wavelength is from one place on a wave to the next exact place on a wave. I want to talk a little bit more about that than what he did. The easiest way to do that is to measure from one crest to another crest. That would be one wavelength. So here's one lambda. So the wavelength here could be equal to, whatever, like 5 meters or so. Another way to do it is from a trough to a trough. Okay, but really what we're saying here is a wavelength is the distance between any 2 points on a wave that are in the same phase. That's what I want to refer to just real quickly here. Phase, which is given by the Greek letter phi, P-H-I, Greek letter phi. And that just means the same angle. You might have recognized that these waves here, this wave here, is actually a sine curve. And we're going to talk, I think we're going to go a lot further into that on the next video. But basically it's a sine curve. And if you have a sine curve like this, which looks like a wave, if you start right here, that's 0 degrees. And then up here, remember, this is like +1, +1, and a -1 down here. can't seem to draw that. -1. So this is 0 degrees. This is 90 degrees, 90 degrees, 180 degrees, or 90 degrees is pi over 2. If we're going to keep these in radians, and we'll have to have them in radians later, but pi over 2, and then pi, and 3/2 pi, 270, right? And then 2 pi, which is 360 degrees. So what we're looking at is any 2 points in the same phase. You'd measure the distance between any 2 points in the same phase. So if this is my starting point here, and this is 0 degrees, this is a 90. So this is 180, this is 270, this is back to 0, and so this would be 90 again. So the distance between here and here is the one wavelength. So between 90 degrees and 90 degrees. Or you could do between 180 degrees and the next 180 degrees. So you can't go from here to here. This is 180 degrees, this is 360. That's not in the same phase. This thing here is moving down. This one here was actually starting to move up. So the wavelength, when he said, 2 points on a wave, I wish he would have maybe used phase angles. So the wavelength is the distance between any 2 points on the wave that are in phase. In phase. That means, particles that have the same displacement from the rest line and are moving in the same direction are to be said to be in phase. So this one here and this one here, both were moving up or something, right? And the same distance away from the rest line. So two angles in phase, the distance between them is going to be how we're going to measure the wavelength. Okay, couple other terms for a longitudinal wave. So by the way, back to a transverse wave. The definition of the transverse wave is that the medium moves up and down. See, the medium moves up and down as the wave goes this way. So the direction of propagation is that way, but the medium is moving up and down like this, perpendicular. The medium is moving perpendicular to the direction of propagation. That is transverse. That's the definition of the transverse wave. So a longitudinal wave, we have these little air molecules that are being compressed, and we have, instead of troughs, we have what we call compressions. I believe he did talk about that. Instead of crest, we have compressions. But instead of troughs, like we had with transverse waves, instead of troughs, we have these places where it's just like regular density air molecules. We call those rarefactions. You might need to know how to spell that. R-A-R-E, rare, and then faction, rarefactions. So basically that means it's spread out more. If you ever breathed rarefied air on the mountain, that means it's very thin air, rarefied air. Okay, lots of vocab I said. All right, so this is like, this would be a sound wave, like someone claps over here, and all the air molecules cram into each other, and then they spread out, and the compression can travel through the air. So this is a longitudinal wave. The medium is moving. It's like compressing over, but then it comes back. So the compressions are going, or the air molecules are like moving this way and then back. And which way is the wave going? It's also going that way. So the definition of a longitudinal wave is that the propagation of the wave and the medium movement is in the same direction. It's in the same direction. That's different than the transverse wave where it was perpendicular to each other. Okay. Let's see. Anything else I wanted to review? Yes, there's several things, I guess. We talked about frequency. The frequency of a wave is so many waves. He called them cycles, so I'm going to call them waves per second. And waves is like counting number. It's like a number, so it's technically not even a unit. So it's basically like 1 over s. And 1 over s is hertz. Okay? Or I guess you could write it s to the -1. Okay? Frequency is in hertz, or waves per second. Period, capital T, that's just, that's not just little t, like time. It's a time period. That would be seconds per wave. But again, wave is not really like a unit, so it'd be seconds over 1, or basically seconds. Okay, so t period is in seconds, frequency is in hertz. And we did an equation to find out how fast a wave is moving, and that was velocity. And he did a pretty good job showing that we, using our old equation, velocity is displacement over time. But what is displacement? How far does the wave move? Well, that's wavelength. That's lambda, wavelength in meters. And if you take wavelength divided by time, you could write this as wavelength, so this time right here is how much time it takes for one wave to go through. So that would be period. I could do wavelength times 1 over capital T period. And 1 over T is frequency. So wavelength times frequency is the velocity. So this equation here, which we're going to use now for this whole unit, and moving on, this is like basically your major equation that you're going to use over and over again. It's really easy. Is the same as this equation. I want you to see that they're exactly the same. Wavelength is your displacement. Frequency is 1 over the period of time. So we can use this to solve a lot of different problems. Oh, by the way, one other thing I wanted to mention is he used the letter F for frequency, and I do too. I think it was very good. I'm glad he did it. It's very smart. But if you look in some physics books, you're going to see a Greek letter that they use for frequency that kind of looks like that. That is called a nu. A nu. Remember, like this was called a mu, right? Okay, this is called a nu. Okay, but it looks, if you look at it, it looks an awful lot like a V, right? So that makes things really confusing. People don't realize that it's it's a nu instead of a V, and so this equation here would look like V equals, nu times lambda, right? And that gets really confusing. So I reject nu. I do not use that for frequency. I use F, just like Sal Khan did. And so if he did it, I'm sure it's right. Okay, so we're going to use this as our equation for velocity to figure things out. Okay, so let's do a couple of problems that were in the book. 6.1 in your book says, in a given medium, what would happen to the velocity? What would happen to the velocity if you increase the frequency? In a given medium, what would happen to the velocity if you increase the velocity of a wave if you increase the frequency of the wave? This is a trick question. And I'm going to tell you that on the competency on the Jedi trial, it's going to be on there. Okay. Some of you are going to get this question, and some of you are going to be tricked. Okay. Normally, what we do with the equations like this is I ask these questions all the time. I say, hey, what happens to this velocity here if you increase the frequency? And it might have seemed obvious that, hey, if you increase the frequency, then you'll increase the velocity, right? Okay. Now that's only if the wavelength stayed exactly the same. And most of the times when I'm asking these questions, that's what you're going to assume. That's what I'm assuming. I'm saying, hey, if you have an equation like F equals ma, and I increase the acceleration, what happens to the force? Well, you'd have to have a bigger force. But every time I've ever asked that, you assume that the variable that I'm not talking about remained constant. Now, this said in a given medium. So here's the key. In a given medium, like I have a spring that we're going to send a wave down or something, okay? In a given medium, you cannot make a wave travel any faster than it travels in that particular medium. Now, if you make this slinky really, really, really thick slinky, then yes, it'll slow the wave down. The wave will have a slower velocity. But if you don't change the medium, waves can only go at a certain velocity through that particular medium. Okay? So in a given medium, you can't change the velocity. The velocity actually stays the same in a given medium. So really, what happens if I increase the frequency in a given medium? Like I go up and down a lot faster here, and I increase the frequency. What's going to happen? Well, the wavelength is going to get smaller, right? The wavelength is going to go down. The frequency goes up, the wavelength is going to go down in a given medium because the velocity actually has to stay the same. Okay? So I hope you got that part. It's a trick question. Okay, in a given medium, you can't change the velocity, right? You can make this go up and down faster here, but all that's doing is making it be more frequent. So instead of having like, this, okay, I can go up and down really fast, and I have like this, right? But what did I do? Here the wavelength was from here to here, crest to crest, right? Okay, and now it's from here to here, right? So the frequency went up, but the wavelength went down, the velocity remained constant, okay, if that's a given medium. Okay, hope that makes sense. All right, 6.1 or 6.2 said, what's the wavelength of light? What is the wavelength of light? Okay, what is the wavelength of light if the frequency of light was 4.5 times 10 to the 14 hertz? What is the wavelength of light if frequency is 4.5 times 10 to the 14 hertz? We haven't talked about light yet, and I don't know if we're even going to get to it this year. I hope, maybe. But how would I do this? Well, I use this equation, right? Velocity is wavelength divided or times frequency. So to find the wavelength, all I have to do is take the velocity of light and divide by the frequency of light. So this problem, nowhere in this problem does it say what the velocity of light is, and that's because it's on your constant sheet, because the velocity of light is constant. Okay, like in air or in a vacuum, the velocity light can never go faster than 3e8 meters per second. It's really, really fast. Okay, nothing can go faster than that. And because it's a constant, a lot of times instead of v, we use the letter c. E equals mc squared. That's c is the velocity of light, 3e8 meters per second. So you need to remember this or have it on your constant sheet. That is always the velocity of light. So if I ever ask any question about any type of light wave, then you know the velocity. Don't think you can't solve the problem. You actually know the velocity. This is like a constant, kind of like gravity. Okay? So the wavelength of this light is going to be 3e8 is the velocity of light divided by 4.5 e14 hertz. And if you calculate that out, you'd get a wavelength of 6.67 e negative 7 meters. That's important. Wavelength of light. Light is just incredibly has a high frequency, and the wavelength then is going to be really, really, really small, so that you can't basically even see it, obviously, because that's you can't even imagine what -7 order of magnitude of -7 is. That's super, super, super small. Okay, now these different wavelengths then mean different colors. So if we don't get to it, now you know different colors. Okay. One last thing I think I'd like to talk about is how much energy a wave has. So I'm not going to get into some big equations here, but you can imagine for a wave, if I had a wave like this, okay, here's a wave that comes in and it crashes into your knee or something on the beach. What if the wave came in and it was like, 20 meters tall, right? So it had a much bigger amplitude. You would imagine that has more energy, and that you would be correct. Now, I'm not doing a real equation here, but I am going to give you some relationships. Energy of a wave is proportional to the square of the amplitude. Okay? Energy is proportional to the square of the amplitude. So if you doubled the amplitude, you're not just doubling the energy. You are actually multiplying the energy by 4 times. If you make this amplitude 5 times taller, okay, you're not making the energy 5 times more. You're actually making it 25 times more. Does that make sense? So you put a 5 in for the amplitude. If you increase the amplitude by 5 times, you're going to 5 squared the energy. So it'd be 25 times more. The same relationship is with frequency. So if we have a wave like this, and then we have a wave, maybe it has the same amplitude, but now it's like this. So we've increased the frequency. See, the wavelength is smaller than it is. Wavelength went down, frequency went up. What happened to the energy? The energy is the same relationship as the amplitude. The energy is related to the frequency squared. So again, if you tripled the frequency, you made this frequency 3 times what it was right there, you tripled the frequency, then what did you do to the energy? You actually made the energy would be 3 squared. So you actually multiplied the energy by 9 times. 9 times as much energy if the frequency was 3 times as much. Okay, so hopefully that was a 20-minute video. A lot of it was review of those first 2 videos you should have watched, and there's a lot more information there that I filled in for you to be able to figure some other things out. So hopefully this unit is going to be a little different. It's not as much math. Sometimes people do a little bit worse on it because it's not as much math and it's a lot more kind of concepts of understanding some of these things. In the next video, we're going to get really big into how these sine curves, these waves, are made and how they're related to the unit circle.